All right, so now we're moving on to section 2 and looking more in depth at solutions. Okay, what does it mean to dissolve and how are covalent and ionic compounds different in solution? So a solution is made by dissolving a solute into a solvent, right? Remember those terms. And so the verb to dissolve is describing an action of the atoms, ions or molecules or whatever is involved of the solute, dispersing their way evenly through the solution. So remember, we're talking about a homogeneous solution, which means the solute is evenly distributed or the mixture is the same. Um, right, so if you have sugar water and it's mixed, the water at the top and the water at the bottom of your cup would be identical, or like a mixture, a concentration of them. And remember that this is a physical process, not chemical. So we're not talking about a reaction actually happening, but there's still action happening, right? So not a reaction in terms of chemistry, but an action in terms of the molecules, atoms moving around. So the process of dissolving is called solvation. So um, that's like producing a solution is solvation, and it's literally just like the solute particle becomes surrounded by solvent molecules. Okay, so if you think about putting, let's say, sugar into a glass of water, right? The sugar in your teaspoon is actually just uh, you know, tons and tons, let's say like on the order of a mole, molecules of glucose, right? Sugar molecules. But the water is a lot more than that. And so when you drop the sugar into the solution and into the solvent water and you mix it, the mixing means every single glucose molecule will be entirely surrounded by water molecules and separated from each other. So it's also like a separation process. And here's a couple of pictures kind of showing that. So this is actually glucose, which is a big molecule, and it's much larger than water. So you can see just kind of like a nice visual of this, like the water molecules basically surrounding the glucose. And here's another example of water molecules surrounding a glucose. And then here's, right, they're like away from each other because they're surrounded by solvent molecules. So if the solvent is water, which is again often the case, that solvation process has a more specific name, which is hydration. So you would say that the solute is hydrated, or it's being hydrated through the process of hydration means it's surrounding by water molecules. Now, eventually we're going to get to the limit of hydration or solvation, and you might start to think about this a little bit right now that if hydration means that the solute is surrounded by water molecules, at some point, if you keep adding solute, there's not going to be enough water molecules there to surround them all the particles, right? And so we will reach some limit of what we call solubility, the amount that can be dissolved. So that'll come up as we go. Um, so water doesn't dissolve everything. As you probably know, you've probably seen at some point like water and oil don't mix. It's even like a cliche almost nowadays. Um, but a lot water and a lot of other things do mix, and oil actually does mix with other things. And so we want to talk about like why does something dissolve something else? Like what allows water molecules to surround that thing? And that has to do with polarity. So if you remember polarity from chapter 4, polarity is if a molecule has slightly positive and negative charges on either side. Remember this symbol, but it just means like a partial charge. Then if there's another polar molecule nearby, it will line up in a similar way. But a nonpolar has no charge imbalance, no partial charges anywhere around, and um, they tend to stick together, just like polar molecules stick together, and they don't like to interact with each other. Okay, and this leads to the concept of like dissolves like. A polar solvent, like water, water is very polar, can dissolve polar solutes. But a nonpolar solute, some sort of oil, like like um, like I said before, something that's nonpolar, even CO2, right, is a linear nonpolar molecule. Methane is highly symmetric and nonpolar. That will not dissolve in water. It'll separate out. There'll be a nice clear boundary between. But a nonpolar solute would dissolve in a nonpolar solvent. Um, hexane is a common one. It's um, a hydrocarbon that's a liquid at room temperature, and so it can be a solvent. But polar solutes like salts, sugar, things like that won't dissolve in a nonpolar solvent. So we get a nice 2 by 2 matrix here, which can be summarized by saying like dissolves like. So polar molecules can be dissolved in polar solvents, and nonpolar molecules can be dissolved in nonpolar solvents. Okay, and again, since water is so special and important to us, when water is the solvent, again, there are special names. Just like there is hydration for uh, solvation when the solvent is water. um, we talk about water a lot. It's the most common type of solution that you'll encounter in medicine if water is the solvent. So these are called aqueous solutions. So we mentioned that before. But then nonpolar solutes can also be called hydrophobic because that means phobic is fear and fear of water. So they're water fearing. They don't like water. They stay away as much as possible. So nonpolar solutes are called hydrophobic. And polar solutes, however, are highly attracted to water, and they're called hydrophilic. So they're water-loving molecules, right? And so these are some important hydrocentric terms that you might want to know. Here's an example of hydrophobic. I thought I had a picture. So water and oil don't mix because the oil here is nonpolar. It's hydrophobic, and so the water would sit at the bottom and the oil would sit on top. Which is more dense, by the way, water or the oil here? Well, since the oil is sitting on top, the water is more dense. It goes down to the bottom. Okay. Um, Another term is immiscible, right? Which means they don't mix, or that there's a clear boundary between them. Okay, so you've been thinking in your mind about the limits of dissolving, right? That I mentioned last slide. That at some point you're going to run out of water molecule or solvent molecules to go around your solute, right? And so this limit, a solution in which the solute no longer dissolves, is known as a saturated solution. So this term saturated is one that has creeped into common language, and people use it just to say, like, if there's a lot of something, right? Like the market is saturated, or culture is saturated with this or that. And here we have a specific definition, right? It's the point at which the solute no longer dissolves. And the reason that point occurs is because there are no more solvent molecules left to surround the solute. So now, by extension, now that we have a definition for what a saturated solution is, anything that has less than that is called unsaturated. So an unsaturated solution has less than the maximum amount of dissolved solute. And the maximum amount, I should say, depends on the solute and solvent. So it's not like there's a set amount for all solutions. It depends on what solute you have and what solvent you have and the relationship between them and how they interact with each other. So you can actually find this is all like in a table somewhere, and we're not going to deal with these actual numbers, but right, if you want to find, this is called the solubility. So the solubility of carbon or calcium carbonate in water. And then you might want to look up the solubility of sodium chloride in water and all these other things. They can be in a table because someone has actually done the experiment. I should add, the maximum amount also depends on temperature, right? And you probably know that from experience, right? If you want something to dissolve, you might heat it up, right? So like the maximum amount that can be dissolved increases as temperature increases. So those are the variables. So in this example here, if we have 100 milliliters of water, and we're going to add 30 grams of sodium chloride, then we would have an unsaturated solution where the 100 milliliters would contain 30 grams of sodium chloride dissolved. But if we added 40 milligrams or 40 grams into 100, we would have a nice little pile of sodium chloride at the bottom, undissolved, that would be 4 grams worth, which means 36 grams dissolved in 100 milliliters of water. So if I were to ask you, what do you think the solubility of sodium chloride is at this given temperature, from the information given here, what is the solubility? What's the maximum amount of NaCl that can be dissolved in 100 milliliters of water? Right, you see it, it's 36, right? Because you put 40 in, 36 dissolved, and 4 was left undissolved. And so once 30 all dissolved, once you hit that 36 grams, no more dissolved, you can think of it like there's no more room at the end, is how I've heard it. So all of the water molecules have basically been used up surrounding what the 36 grams. So the solubility of NaCl would be 36 grams per 100 milliliters of water would be one way you could write it. And then look, it's a ratio, which would be a conversion factor. I'm not going to actually have you do that right now or this time, but you recognize this now, whether you want to or not. Maybe you have nightmares about it, but it's always when you write a fraction like that, it can be used as a conversion factor. Okay, we're approaching 15 minutes, which I usually is like my cutoff, but I want to roll through just a little bit longer so we can just finish this and be done, and then move on to the next section next time. So we'll keep going until we're done. And so we have an unsaturated solution. Just these first two is kind of a review. The last slide means that more solute can dissolve. Once you hit the saturation point, no more solute dissolves, but it's possible to have a supersaturated solution which has more than the maximum amount dissolved. And eventually, what you'd probably end up with is crystals growing because this is an unstable solution. So there are a few ways you can get a supersaturated solution, and one would be the fact that solubility is temperature dependent, right? So if you increase the temperature, you can dissolve more. So if you heat up a solution and add just to like the solubility, add solute, and then as it cools down, the solubility, the maximum amount that you can dissolve decreases, but you already had more than that now dissolved in it. And so this supersaturated type solution can stay dissolved, but then it's very unstable. And if you can like flick the side of the beaker or add a little bit more to it, and crystals will form out of solution. And it's really cool. So I have a cool video, not of me, but it's on YouTube of this supersaturated process and then a crystal grow, and it's like literally 1 minute, but I can't figure out how to insert a video into this. So I'll post a link to it. So there'll be a YouTube link next to this on Brightspace showing a 1 minute supersaturated solution. Or you could just go to YouTube yourself and just type in supersaturated solution, and you'll find some that are like the short, they it doesn't have to be very long, where they take a solution, add a little crystal, a tiny little piece, and then you see crystals grow. It's pretty cool. Um, Supersaturated solutions. Let's see. So there's another thing that you can look up on your own if you dare. Kidney stones and gallstones are examples of precipitates that form from out of supersaturated solutions. So precipitate is just a fancy word for a solid that forms. Um, I've considered putting pictures of these up, your nursing students, um, but I'm gonna go ahead and let you go look them up on your own if you dare. You should be able to handle it. Look up kidney stones and gallstones. Those are also examples of crystals growing out of supersaturated solutions. Okay, I want to finish up looking specifically at um, ionic compounds that are in the solvation of ionic compounds. If you remember, an ionic compound takes like a lattice form. So sodium chloride here, again, that's always our example, right? Um, Ions are attracted to each other in a 1-to-1 ratio, so Na plus Cl minus. When it's hydrated or solvated, what happens is that they get separated out. So the plus, the cation of Na plus here, has water molecules surrounding it with so remember water is polar, so it has a partial negative charge around the oxygen, partial positive charges on the hydrogens. So the partial negative lines up um, towards the positive of the cation, and when you have an anion with a negative charge, the positive charge of the hydrogens line up. And so you get this cool ion dipole interaction. And this ion dipole interaction leads to what we call electrolytes. So electrolytes are ionic compounds that are dissolved in aqueous solutions. Due to the charges involved here, electricity can flow through this solution from positive to positive to negative, and so on. So that's why they're called electrolytes, because electricity can flow. So there are some physiologically important electrolytes that we must have in our bodies, and they come through the food that we eat and through salts. So you can see them here in this list. You don't need to talk too much about that right now. We'll move on. But when the key point is that when ionic compounds dissolve, it splits up into aqueous cations and aqueous anions. right? And so it's split. It's not a chemical reaction though. Remember, it's still just a physical separation. Because even an ionic compound is just kind of physically they're brought together next to each other due to the charges. Um, but a covalent compound, when it dissolves in water, it stays as the same covalent compound. It's just now surrounded by water, which we say is aqueous, right? So a little bit of a summary, a distinction between ionic and covalent compounds when they dissolve. An ionic compound will produce aqueous cations and aqueous anions when dissolved, but a covalent compound dissolved in water just produces an aqueous covalent compound. So this was how I ended the class last time I did these notes. I'll put this in your question so you can still expect it later. But right, what's the difference about an ionic compound and a covalent compound when each dissolves in water? So we just talked about that, and we'll leave it there. So I'll get this posted up, and then next time we will um, look at solution concentrations. All right, take care.